Greetings and salutations, magical chemists. Today we're going to talk about calorimetry. Calorimetry is the experimental technique that we use when we want to measure the change in energy of either a chemical reaction or a phase change. The trick is, it can be hard to measure the chemical change of an actual reaction. So what we do is we take our chemical reaction or the phase change that we're trying to study and we put it into contact with a water bath. And then we measure something that's really easy to measure the temperature change of, the water. Now the trick is, we recognize since the system we care about is like the object or the reaction, well, whatever energy is lost by the object of the reaction must be gained by the water. So if you can measure the change in temperature of the water or the change in, and then calculate Q using, of course, MCAT, then you automatically know what the energy change was for that object. Now it could be an object or it could be a reaction. So basically we're just setting MCAT equal to MCAT, as long as you remember that one side has to be negative. And honestly, it doesn't matter which side is negative. It's just a lot of things we measure are exothermic, so the water gets hotter. That's why I tend to keep my positive sign with the water. But it doesn't matter. As long as one side is positive and the other side is negative, mathematically, you just solve for whatever you're looking for, and it's just a delicious pile of algebra. Of course, you'll remember the specific heat of water, which should be given to you, but occasionally I forget, is 4.18 joules per gram degrees Celsius. So that's what we plug in for the specific heat capacity of water when we're setting up our MCAT equals negative MCAT. Now, even though technically we're not writing a formal lab report about calorimetry, it's still really important to understand the experimental errors that come with calorimetry. You'll see these experimental errors in evidence when you go ahead and do the Cheeto lab in class. Because we make the assumption that whenever the energy lost by the object or the reaction, that we are capturing all of it in the water bath. But that's not quite true. Our calorimeter, or container, oftentimes some kind of cup, or in the Cheeto lab it was a can, well, that's also capable of absorbing some of the energy change given off by our reaction or object. And of course, there's no perfect insulation, so heat can be lost to the air as well. So even though we pretend all of the energy, the heat, was absorbed by the water, some of it gets lost to other things. In that case, when you're measuring the temperature change of the water, the temperature change of the water isn't as big. Delta T of the water is going to be smaller than it would have been if it absorbed everything, which means Q, when you calculate it, is going to be smaller than what the actual heat exchange was. So just watch out for that. Pretty much, whenever you're doing a lab with calorimetry, inevitably the error leads to a smaller calculated Q than the actual reality because of the lost energy. Well, okay, it's not lost. We know where it went, but it wasn't measured. Now, there are two types of calorimeters that you will come across. The common one used at a high school level is called a coffee cup calorimetry, or calorimeter, because, as you probably guessed, it's made with coffee cups. These are actually surprisingly effective if you use them right. Coffee cups are meant to be insulated, and if you use two of them, then you get a double insulation. So do not insult the coffee cup calorimeter. I've even had college classes that use coffee cup calorimeters. They can be very, very effective. However, they are not quite professional level. And if you want to measure the energy exchange, just like how we do with the Cheeto lab, you're trying to measure the energy of the Cheeto itself, well, they need to do that for the calorie content on a food bag. But they don't want to use a coffee cup. They need to be pretty dang accurate. So they use what's called a bomb calorimeter. That is not nearly as exciting as it sounds, because you don't really see anything. It's just a giant metal container, aka the bomb. It just entraps the reaction on the inside. It's just really, really well insulated. So they sound really exciting, but actually, because I've used one, they're not necessarily exciting. You don't see anything happening. They just are really good at providing great insulation. But mathematically, regardless if you're using a coffee cup calorimeter or a bomb calorimeter, the math remains the same. Speaking of the math, let's go ahead and try a type of problem that you might be asked about calorimetry. All right, so we are taking a 5.037 gram piece of iron. very specific, I know, and we heated it up to 100 degrees Celsius. And then we put it into a coffee cup calorimeter. Now the coffee cup calorimeter originally contains 27.3 grams of water. Remember, calorimeters, we need a water bath. And that water is originally at 21.2 degrees Celsius. Now, after we put in the piece of iron into the water, the final temperature ends up being 22.7 degrees Celsius. Now, I want you to realize this is the final temperature of both the iron and the water, because once you put the iron in the water, well, they equalize in temperature. That's the whole point. So notice we have an initial temperature of our iron, which is given. So this is our initial temperature of the iron. And we have an initial temperature of the water. So it's important to recognize the information that you're being given here. So we have separate information. We have information for iron and we have information for water. I don't know why I wrote water, but so, and then again, we have the mass. We have the mass of the water. Whoops, that's supposed to be an H. And we have the mass of the iron. So we've got a lot of different pieces of information in here. So mass of iron. And we need to combine this all together into a delicious whole. So I find it helpful myself to always go ahead and start off by writing my calorimetry equation, which is simply that Q. Well, let's write the generic one up here. The generic one is just that the Q of your water is going to be equal to the negative Q of your object or reaction. So in our case, we of course have Q of water. If it's calorimetry, you're always going to have Q for water. And it's going to be equal to the negative Q of the iron, because this time we are specifically looking at the negative Q of the iron nail. So once we know that, now we can start looking at our equation, because of course Q is equal to MCAT. So we've got, MC delta T on both sides. So there's a lot of variables going on here, but really, as long as you're careful to just plug in the given numbers in the right place, this is simply straight up algebra. Notice what they're asking you to solve for. Specific heat capacity of the iron, this guy. So that's going to be your unknown variable, which means we sure as heck better have numbers for everything else. So let's go ahead and plug in all the values that we have. First, we'll look at the information for the water. So remember, they didn't tell you in the problem, but it was in your notes. The specific heat capacity of water was 4.18. And then the final temperature, of course, is the same for both of them. And this was the initial temperature of the water. So now we can go ahead and plug in the values that we know. We don't know all of them, but the values that we do know for the iron on the right-hand side. Don't forget to keep that negative sign. So once we've plugged everything in, we just need to simplify down all of our numbers, and then we can solve for the specific heat of iron. So I'm going to go ahead and combine everything on this side of the equation, because that's just going to spit out a number. So go ahead, use your calculator to do that, and I'll do the same thing over here. I'll be able to combine this number and multiply times that number. So that'll simplify it a lot. All right, now notice I had a negative sign, because of course Q equals negative Q for calorimetry. But when I subtracted 22.7 minus 100, that's another negative. So the negatives cancel. That's one of the reasons I usually put the negative with the object. So now we can just go ahead and do a little bit of division to solve for the specific heat of iron. And once I plug that into my trusty calculator, and gotta watch out for sig figs. In this case, I only get to keep 2 sig figs. You might be looking at this going, wait, but why? It turns out, sig figs, it's the subtraction, 22.7 minus 21.2. Following sig fig rules, when you take 22.7 minus 21.2, you get 1.5. That only has 2 sig figs. Yay, sig figs. So what that means is your final answer only gets 2 sig figs. So ultimately, you will get 0.44 joules per gram degrees Celsius for the specific heat of iron. So calorimetry questions, as you can see, definitely involve a lot of algebra, but there's nothing really tricky about it. You just have to be very careful about plugging the right numbers into the right places. We're not going to do all of number 3 together, but we're going to just set up part of it, because number 3 pretty much is the most algebra you could ever do on a calorimetry problem. I am sure you are totally excited. So let's take a look. In number 3, again, they're giving you lots and lots of information. So we've got a 376 gram sample of gold, and it's starting at 400 Kelvin. And of course, we place that into a coffee cup calorimeter. What else would you do with your gold? And this coffee cup calorimeter contains 50 milliliters of water at 300 Kelvin. Now remember the thing about water. Water has a density of 1 gram per milliliter. Because of that, 50 milliliters is 50 grams. So watch out for things like that, because, you know, we're nice, we're friendly, chemists love you, so we give you sneaky things. All right, now what we want to find is the final temperature of the water. And we're going to assume that no heat is lost to the surroundings. Even though we know that's not true, we're going to pretend. And it gives you the specific heat of gold, which is good, because if they didn't tell us, we wouldn't know what it is. Of course, we already know the specific heat of water. So now we have, once again, the classic, where we're going to set up Q of water is equal to negative Q of our metal. And gold, by the way, is AU. AU. So, well, yeah, anyway, so it's AU. So we're looking at Q of H2O is equal to negative Q of AU. So now we can just go ahead and plug in the given numbers. But you'll notice something. So let's go ahead, let's plug in what we got, and then we'll take a look again. So first we plug in everything we know for water, including the specific heat capacity. But notice, we don't have the final temperature, so you can't calculate delta T. And then we're going to go ahead and plug in all the values we have for gold. All right, we've got all of our numbers plugged in. Everything else is just algebra. Yay, delicious algebra. So I'm not going to solve this for you. I know you know how to do algebra, otherwise you never would have survived this class this far. But I will give you a hint. Combine these numbers first, and then you totally have to distribute. Yay, distributive property, totally a thing. So again, I'm not going to solve this for you. However, I do want to tell you what the answer is, so you'll be able to check to see if you're right. At the very end, after you do lots and lots and lots of math, you should get a final temperature with 3 sig figs of 319 Kelvin. And remember, we can keep the temperature in Kelvin. We did not have to convert to Celsius because the conversion, it ends up being the same mathematically. So we're all good. If you convert it to Celsius, you won't be wrong. So that is the answer, so you can check. I'm going to let you do all the fun and exciting algebra.